Hey guys, so this is going to be the first video in a series covering basically everything you need to know about physics on the MCAT. And the goal of this series is to present all the information in the Kaplan textbook for physics. It's probably the most commonly used physics textbook for the MCAT and the one that I used, but to present it in a manner that's a lot more condensed and a lot more visual. It's already hard to get through a textbook that long and very time consuming. And I already find that people spend too much time on content review for physics. It's doing the practice that really helps you to both master the equations and enhance your your problem solving skills. So I'll try to keep these videos to about a half hour per chapter of the Kaplan textbook. And I'll aim to post a video about every 5 days or so. So, hopefully we can get through all of physics in the next month and a half, 2 months. And without further ado, I'll get into the first chapter of kinematics and dynamics. I'll begin by briefly covering the SI units for this chapter. And SI units are basically the units that you want to be using. So if you get any other kind of units, when you're doing the equations, you want to convert back to these units. And the relevant SI units for this chapter are meters, kilograms, and seconds, and those measure obviously length, mass, and time, respectively. So if you're given, for example, the speed of a car in kilometers per hour, you'll want to convert that to meters per second. And actually, just one note, if you guys want to see a math video, either kind of everything you need to know about math in the MCAT, or even just some of the tips and tricks that I use on these physics questions in terms of the math side of things, let me know in the comment section and I'll be happy to make that happen. Next up, I want to cover the difference between a vector and a scalar, because that's a very important distinction to make, not just in this chapter, but probably in every chapter that follows this one. And the main difference is that a vector does depend on the direction, and a scalar is simply a measure of the magnitude and does not take into account direction. So time, for example, is a scalar because time is always going to pass, and it's going to pass the same way, whether you're moving, for example, to the left or to the right. But what about distance versus displacement, for example? Those are both measures of how far you're going. But the distance is, again, irrelevant of direction. So I'll give you an example. If we have a man that's walking, let's say 10 meters to the right. So this man's walking 10 meters to the right and then 10 meters back. The distance here is a total of 20 meters, right? 10 plus 10 is equal to 20. And again, the direction here is not relevant. So 10 meters to the right is still 10 meters, and 10 meters back to the left is still 10 meters. Whereas the displacement here is actually 0. So displacement is a measure of how far you end up, essentially, compared to where you began. So in this case, the direction does matter. If we assume that the right is positive, then moving to the left would be moving 10 meters in the negative direction. And those cancel out. 10 minus 10 in this case is equal to 0. So this man, walking the same path, had a distance of 20 meters covered, which is, again, a scalar, and the vector measurement of displacement was a total of 0 meters moved. So one important skill in the MCAT is to be able to combine multiple vectors, or to basically add two measurements that don't necessarily have the same direction. In this case, we have 10 meters to the east and then another 7 meters to the north. And the way that we combine these two vectors, which I have these two arrows over here to represent, is we add them from tip to tail. So essentially the tip of that one arrow to the tail of the next one. And you can do that either that way, or you can do it that way. Either way, you'll get the same resultant vector, which would look something like this. And that resultant vector, you can solve using a squared plus b squared is equal to c squared. And when I go through this example quickly, I'm going to show you a quick math tip that is extremely helpful on the MCAT, and that's basically the power of estimation. So on the MCAT, close enough is usually good enough. Because it's a multiple choice test, as long as you have an answer that's quite close to one of the given options, that's usually going to be the correct one. And of course, you have to do that in an educated way, and I'll show you an example of that here. So a squared plus b squared is equal to c squared can be rewritten as, c is equal to the square root of a squared plus b squared. And again, if any of the math here isn't clear, just mention it in the comments, and I can either address it there or eventually make another math series or video. But we can solve c using this equation. C is equal to the square root of 10 squared, which is 100, plus 7 squared, which is 49. And then we're left with c given a value of 149, which is not something that's easy to do in your head or without a calculator. So this is an example of where making an appropriate estimation is actually extremely effective. And here we can think of a number that would give us a perfect square, like a number that's easy to square root, that is pretty close to 149. And in this case, a good option would be 144, the 12 squared. So if we estimate c as 100 or the square root of 144, then we can say that c is roughly 12. But then the important next step is to look at whether c is a little bit greater than 12 or a little bit less than 12. And here we see that we kind of rounded down. We assumed that instead of 149, it was actually 144. So our answer should be a little bit greater than that estimation where we rounded down. So we know that c should be a little bit greater than 12. And the actual answer, I believe, is about 12.2. And if that was on the MCAT and the answer was 12.2, using your estimate, you would have 100% been able to get the correct answer. Okay, so let's get into some actual equations. The first thing that we're going to cover is velocity, which is given that little arrow on top of the v, and that just means that it's, as we mentioned before, a vector. So it does depend on direction. And the velocity has an equation, v is equal to delta x over delta t, which is the change in position over the change in time. And the reason the change in position is important is because, again, we're not just looking at the total distance covered. We're looking at where they ended up versus where they began. So if we take, for example, a girl that is going to be walking a path that looks something like that, right? We're not necessarily looking at the total distance traveled, but rather the change in position from the end compared to the start. So let's say that this is 10 meters, and this took her 2 seconds. Then the velocity is going to have, or an average velocity of 10 over 2 or 5 meters per second. Again, here the units are very important. If it's given in anything other than meters and seconds, you're going to have to convert back. I also want to touch on the way that graphs work for this type of an equation, because the ability to interpret graphs in the MCAT is quite important. So in this case, let's say that we have a position time graph. So on the y-axis is the position, and on the x-axis is time. Let's say that our graph looks something like this. The slope of the graph, and this is a rule that applies to all these graphs, the slope of the graph is always going to be your y-axis divided by your x-axis. So in this case, the slope of the graph at any given point is x divided by t, or the change in x divided by the change of t. And notice that this is the same as our equation over here, right? So the instantaneous velocity is actually the slope of this graph at any given point. So let's say we look at t is equal to 5 seconds, which is right over here. If we were to draw a tangent line to this point, that would be our velocity at that time of 5 seconds. And this rule where the slope is equal to the y-axis divided by the x-axis applies to any kind of graph. And we'll go over in a future slide what the area beneath the curve is going to represent as well. I'm now going to talk a little bit about acceleration, which if you're following along with the Kaplan textbook, you'll notice that the order I'm going to cover the content in this chapter will differ just a little bit. I think this is a bit more coherent. So acceleration has an equation where acceleration is equal to delta v, or the change in velocity, over delta t, the change in time. And once again, I'm going to cover the way that a graph here would look. Let's assume now that we have a velocity time graph. So velocity is measured on the y-axis and time on the x-axis. And let's say that our graph looks a little bit like this. So again, we can find the slope of this graph by looking at the tangent line at any point. So let's say, for example, this is maybe at 3 seconds, that's going to be the tangent line. And the tangent line, or the slope, is always going to tell us the value of the y-axis divided by the x-axis. And in this case, the y, or v, divided by the x-axis, or t, we notice is, once again, the same as our equation. So in a velocity time graph, the slope of your graph is going to give you the value of the acceleration. But now let's also look at what the area beneath the curve represents. So let's look at the time between, let's say, 3 seconds and 10 seconds over here. The area under the curve actually represents the y-axis multiplied by the x-axis. So the slope was y divided by x. Here, they can be multiplied together. So v times t is going to be represented by this area beneath the curve over here. Now, what is v times t? In our last equation for velocity, we had v is equal to change in position, or x, divided by time, or t. So if we rearrange this, we see that v times t is actually equal to x, or displacement. So in a velocity time graph, the slope will give you the value for the acceleration, and the area beneath the curve is going to give you the value for the displacement. All right, so now we're on a slide that's probably going to make a lot of you guys groan. The kinematic equations are something that definitely can seem daunting, but honestly, there's only 4 main equations that you have to know, and 2 of them, once you understand this, can kind of become common sense. In my opinion, only these 2 bottom equations over here are actually necessary to memorize. And I'll explain the 4 of these briefly. The first one over here is simply a measure of what the final velocity, or VF, is going to be after a moment of, or after a period of acceleration. So we're going to have an initial velocity VI, and then the object is going to begin to accelerate with a value of a over a period of time represented as t. But I'll show you why this is not necessarily an equation that you have to actually memorize. And that's because, given the equations that we've already learned, this can be derived pretty easily. We learned that acceleration, or a, is simply the change in velocity divided by time. So if we actually rearrange this, we can put velocity over to this side, right? So it'll be essentially VF minus VI, or the change in velocity. And we can divide both sides by time, and we get that. So this is basically the equation that we've already learned for acceleration. Now, this second equation is also one that can be derived, or you can kind of just use your logic to get through. But it's essentially a version of the equation we've already learned for velocity. And we learned that velocity is equal to delta x divided by delta t, or that when it's going to be rearranged, displacement is equal to velocity times time. And this is the same thing. We just have a term over here for the average velocity. And we find the average the way we would find the average between any other 2 numbers. We would add them up and divide them by 2. So this is the sum of the 2 velocities. Let's say that we begin at 2 meters per second, and by the end of the trip, we're at 10 meters per second. This term over here simply represents the average of the 2. So the sum of 2 and 10, or 12, divided by 2, which gives us an average of 6 meters per second. And this would go into the equation as normal. And what you can see here is that overall, this equation is simply a measure of the average velocity multiplied by time. Okay, so the bottom 2 equations are actually ones that you'll have to memorize. And in my opinion, this one over here on the bottom left is probably the most important one, and at least the one that I tend to use the most in the equations that I encounter. But overall, the key here is really just to look at what you have, what you're given in the question, and what is unknown. And to be able to solve one of these equations, you can only have one unknown. For example, if we're trying to solve for the initial velocity, then we have to know all the rest of these. The rest of those terms all have to be known. We can never solve an equation when there's more than one unknown. So when choosing between these 2 equations and deciding which one to use, you should first list out knowns as well as the unknown. So let's assume that we have the displacement, x, we have the initial velocity, and we have the time. So these are all knowns. And we're trying to solve for the acceleration a. This is an unknown. Now let's look at the 2 equations and compare them and see which one we'll be able to use to solve the question. So we have displacement, that's on both of the equations. We have the initial velocity, and I should have written an I over there. So we have the initial velocity, that's also on both of the equations. And we have time, which only exists on this first equation over here. So now let's look at what's not known in both of these equations. In the first equation, the only unknown is the acceleration, which is what we're trying to find. That's perfect. That means that we can use this equation over here. Looking at the other equation, however, we see that both the acceleration and the final velocity are unknown. So we're not going to be able to isolate for acceleration and solve it. So in this case, the first equation would be the appropriate one to use. All right, so here's a kinematics problem that involves vertical motion, so one where we have to take into account gravity. In this problem, a ball is being thrown upward at 12 meters per second, so it has an initial upward velocity of 12 meters per second. And what's very important to note is that if we assign the upward direction as positive, then gravity, which is going to act downward, must be given a negative value. So gravity is going to cause the ball to experience a downward acceleration of 9.81 meters per second squared. And that must be written as negative because it's acting opposite to the direction of the ball's initial movement. Now let's look at our two equations and see which one might be fit to answer this question. Let's begin by listing the knowns. So we're given the initial velocity of 12 meters per second, which exists in both equations. We're given the time, 2 seconds, which only exists in this first equation. And we're given the acceleration, which is negative 9.81 meters per second squared, again existing in both equations. So the first equation here works perfectly because we have our unknown, the displacement, which is what we're trying to find, and the rest of the variables are all known. But the second equation is not going to work here because we're trying to find the displacement, which is an unknown over here, but we do not have the final velocity. So there's a second unknown that makes that equation not usable for this particular problem. Now I'm going to run through the math quickly for this equation, and again show you kind of how estimates can be an important step in these types of problems. So the displacement over here is equal to the initial velocity multiplied by time, which is 12 times 2, or 24, plus half of at squared. And this part can be a little bit tricky to do in your head, and I'll show you a bit of a shortcut. So rather than writing minus 9.81 as a, we're going to round a to minus 10. So this is going to be 0.5 times negative 10 multiplied by t squared, and 2 squared is 4. Now all of a sudden this is a lot easier to do in your head. But what's important to note here is that the value of this term in our estimate is going to be a little bit greater than it actually is because we used minus 10 as opposed to minus 9.81. So we now have x is equal to 24 plus minus 20, which is going to give us about 4. So x is equal to about 4. But again, this term over here, the absolute value of this term is actually a bit less than 20 because, again, we rounded 9.81 up to 10. So it's actually going to be 24 minus a number a little bit smaller than 20. So we get a value of a little bit greater than 4, or x is going to be slightly greater than 4. And now when we look at our answers, we see an option for 4.4 meters. And there's no one way to do mental math on the MCAT. This is just a method that I like to use, but really whatever works for you is absolutely fine. And like the math here was still quite simple, like you could have actually solved the exact value for sure, but I just kind of wanted to show how this method can be applied. I'll split this chapter into 2 different videos just because it's quite a long chapter and it kind of serves as the basis for all the rest of the physics that we're still going to cover. But the most important takeaway from this video are the 4 different kinematics equations. And if you want, you can either make a sheet with these equations or even put these equations into your own Anki deck. But these equations can all be used in different contexts. The first one's helpful when we don't have the displacement. The next one when we aren't given the acceleration. The third equation when we don't have the final velocity. And the fourth one when we are not given the time. Because again, only one unknown can exist for us to be able to solve the equation. The next video is going to talk more about forces and free body diagrams, as well as some applications of all of this. So things like inclined planes and projectile motion. Also, this is my first time doing this, so I'm super open to any feedback. Please don't be shy to leave any suggestions or any ideas that you'd like to see in the comment section, and I'll do my best to incorporate them in the future. So that's it for part 1 of chapter 1 of physics on the MCAT.